Hello everyone. In this video, we are going to study chapter 16, section 16.7. In this section, we are still going to talk about relative motion, general plane motion, and we have some rods connecting together. But in this section, we're going to add in accelerations. Okay, we're going to resolve the acceleration of a point on a body into components of translation and rotation motion, and we're also going to determine the acceleration of a point on a body by using the relative acceleration analysis. The velocity equation, we've already seen it, taking the first derivative of the velocity, that will give us the equation for the acceleration. And notice that whenever we talk about the acceleration, it always refers to problem like this will always refers to two components. One is tangent component, the other is normal component. Tangent component changes the magnitude of the velocity. Normal component changes the direction of the velocity. So graphically we break that into two parts, right? The translating AA is this one that's translating. We assuming there's no rotation, and then second part we have rotating, and the rotating we have the tangent component and the normal component. Relative tangential acceleration component, there's the tangent component a b slash at, and then the normal component a cross r b slash a, and then that's the normal component. The relative normal acceleration component a in the direction is always from b towards a. Since the relative acceleration component can be expressed as a b slash at, which is alpha times the radius, and then the normal component will be negative omega squared times the radius. Relative acceleration equation we are writing like this: ab equals aa plus alpha cross rb slash a minus omega squared rb slash a. Notice that the last term in the relative acceleration equation is not a cross product. It is a product of a scalar squared of the magnitude of the angular velocity, and the relative position factor rb slash a. Also over here, the omega squared is the square root of magnitude of the angular velocity. In applying the relative acceleration equation, the 2 points used in this analysis, A and B, should be generally be selected as points which have the known motion, such as the pin connections with other bodies. In this mechanism, point B is known to travel along a circular path, so AB can be expressed in terms of its normal and tangent components. Note that point B on link to BC will have the same acceleration as point B on link AB. They're connecting together. Whatever the motion will be the same regardless of if I'm looking at from link AB or from link BC. That's what they're trying to say. Another thing is that since point C, it's got a piston motion, and it can only move along the direction of the piston. That means it moves along a straight line, moves around a straight line for that piston. So that means the AC is directly horizontal. Procedure for analysis, we're going to establish a fixed coordinate system, draw the kinematic diagram of the body. We're going to indicate AA, AB, omega, alpha, R, B slash A. If the points A and B moves along curved paths, then their acceleration should be indicated in terms of their tangential and normal components. So your AA equals AAT plus AAN, and then AB equals ABT plus ABN. We're going to apply the relative acceleration equation. There's your AB equals AB plus alpha cross r b slash a minus omega squared r b slash a. We've seen this equation in the previous slides. If the solution yields a negative answer for an unknown magnitude, this means that the sense of direction of the vector is opposite to that shown on the diagram. Take a look at this. We have this rod that is leaning against the wall. We know that the direction, we know that the direction of the B is when it comes down, right? When the AN comes down, BN will go to the right. So that means the velocity for the B will only have the I component, positive I. And then the velocity for the acceleration will only have the J component coming down, negative J. So I know the acceleration 5 meters per second square, and then we know the velocity 6 meters per second. And then so let's put some equations together. First thing is that using the velocity of A, and we know that the instantaneous velocity is right here based on our previous video and previous section. Omega, we can look for the angular velocity by taking the linear velocity VA divided by 3 meters, which is the distance here. If you wonder where that comes from, this is a 3, 4, 5 triangle. It's 4 over here, 5 is the hypotenuse. That means this end right here is 3 meters. That's where that 3 comes from. So 6 over 3 gives me the angular velocity of rod AB, 2 radians per second. All right, so keep going. Since the A and B both move along straight line, we can know A comes down negative 5J, AA comes down negative 5J meters per second square. AB will be only on the horizontal direction, and it's ABI, right? We assume it's positive to the right. And then plug into our equation. Now keep in mind that it looks like it's one equation, but since it's a vector equation, toward the end, we're gonna separate the I and the J's to really, there are two equations in there to help us solve two unknowns. And the two unknowns are your AB and your alpha. Okay. That's our first example. Keep going. We're going to talk about bodies in contact. Typically, the bodies in contact, we talk a lot about the gears. Consider two bodies in contact with one another without slipping, where the point in contact move with different paths. So in this case, the point that we have in contact at this point A right here, they will share the same linear velocity at that location A, share the same linear velocity. In this case, the tangent component of the acceleration will be the same. A tangent equals um, the other, so it refers to this A and that A, right? So tangent component of the two gears will be the same, which implies the alpha B times RB equals alpha C times RC, because this alpha times R gives me the linear acceleration AB, and then over here gives me the linear acceleration AC. These will be the same thing. Oops, sorry. So let me erase that. Yeah, there go better. And the normal component of acceleration will not be the same. Keep in mind that normal acceleration is pointing toward the center of the circle. Normal acceleration changes the direction. Only the tangent component will be the same, not the normal component. Another common type of problem in counting dynamic involving rolling motion without slipping, example, a ball, cylinder, or disc rolling without slipping. This situation can be analyzed using relative velocity and acceleration equation. As the cylinder rolls, point G will be the center, moves along a straight line. We've seen it before. If omega and alpha are known, the relative velocity and acceleration equations can be applied to A. At the instant A is in contact with the ground, the point A is the instantaneous center of the zero velocity. However, it is not a zero of the zero, it's not zero acceleration, but it's zero velocity, the point that's in contact with the ground. We talked about it before. Keep going. Since no slip occurs, VA equals 0 at that moment, and A is in contact with the ground. From the kinematic diagram, we have this equation, VG equals VA plus omega cross RG slash A. So we plug in our values, we get VG equals omega R, or VG equals omega RI, because VG only has horizontal component. Since looking at, let's take a look at acceleration. Since G moves along a straight line, center of this plate right here, the center of the circle moves in a straight line path horizontally. Just before A touches the ground, the velocity goes downward. Just touches the ground, velocity A goes downward. And then so I kind of draw it at the angle, but imagine it's very, very close to it. It's going straight down, not at an angle. It will be straight down, just like gravity going down. And then just right after the contact, the velocity will going straight up. So thus this point A accelerates upward as it leaves the ground. So we come up with this equation, AG equals AA plus alpha cross RG slash A minus omega square RG slash A. So over here, AGI equals AAJ plus negative alpha K cross RJ minus omega square RJ. Evaluating and separating the I and J component, separating them, you have AG equals alpha R, AA equals omega square R, or AG equals alpha RI, and then AA equals omega square RJ. So let's take a look at some more examples. So we have a gear with a center at O, rolls on a fixed rack. We've seen something similar in the previous video, the previous section. Now today in this problem, we're going to add in acceleration. Okay, we know the alpha 6 radians per second square. We know the omega is 12 radians per second. And then we know the radius here is 0.3 meters. We're looking for the acceleration to point A at that instant. So plug into our equation. We know the initial acceleration is a0, not initial, sorry, AO. Acceleration at point O is 1.8 meters per 1.8 meters per second square. And then alpha negative 6k, and then the r relative position of A with respect to O. Pretty obvious. You have O right here. Your A will be just right on top of it, so it's positive 3j. And then minus omega squared, which will be 12 squared, multiplied by another 0.3j. Okay, put that together. I got acceleration AA. Last example here. So this one says, I know the member AD's omega and alpha, angular velocity and angular acceleration at that instant. We're looking for the velocity and acceleration of the slider block C. Okay, so since AB and BC are connecting by B, we can use rod AB to calculate what's going on for point B. And then from whatever is going on at B, we can figure out what's going on with BC and then relating to the block C. Okay, that's what it is. So VB is going to be omega AB times the radius. Okay, does not surprise me. Acceleration will be omega squared divided by omega squared RB slash BA, and then this gives me the linear acceleration, and then tangent component will be alpha RB slash A, and there we can get VB equals negative AI, because the B, we know that it's going horizontally to the left. That's only the I component is negative. Acceleration B acceleration B goes to acceleration of B, you will have the normal component and the tangent component, right? So we're putting the 32 and the negative 10 together. That will give us the actual acceleration, both normal and tangent. Now keep going. Now that apply the relative velocity equation between the points B and C to figure out the angular velocity of link BC. Now whatever is going on with B, and then link together with the B, omega BC and RC slash B, that will give us an equation here. What I do want to emphasize here is that what's going on with this term right here, VC. VC has its own magnitude, but we know that the angle right here is following by this 3, 4, 5 triangle. So in other words, let's say VC is like this, right? I don't know what the X and Y, the I and J component is, but I know that based on that 3, 4, 5 triangle, I know that the horizontal component of that VC is going to be this horizontal component of that triangle. So the horizontal component of that VC, so over here, use your VCX. And let me write that VC a little better, just a little better, since I'm adding. So over here is your VCY. Okay, so over here it's going to be your VC overall. VCX is going to be the X component if you close the triangle like this. So your VCX is going to be 4 out of that 5. 4 out of that 5 of the entire VC. That's where that negative 0.8 come from. And since it's going toward the left, you have negative. Okay. And then similarly, the Y component VCY, is going to be the 3 out of that 5 of that VC. That's where that 6 comes from. I meant to write a 5, not a 6. So that's where the 0.6 comes from. And it's negative as well because I'm coming down. It's negative 3 over 6. That's where that comes from. So that overall multiplied by VC. Okay, so be careful. Now, and then we separate the I component and the J component. That will help us calculate the omega BC and the VC. And then keep going. We have another acceleration, another equation for the acceleration. Still acceleration, follow this 3, 4, 5 triangle, separating the I and the J component. I can get the AC and the alpha BC as well. Okay, that's all I want to show you in this video. Hope you find it helpful, and thank you for watching.